Another concept we have come across before in this course was congruence. And for integers a, b, and m is positive, we say that a is congruent to b modulo m if m divides the difference between a and b. Now it's stated as a minus b here, but we could also have written this as b minus a. Simply, when m divides the difference between a and b, and we say that a and b are congruent modulo m, and this is the notation we use. And based on this definition, we have the following theorem. When a, b, and m are integers and m is positive, um, a is congruent to b modulo m is equivalent to saying a and b have the same remainders when divided by m. Okay, so they simply have the same remainder when you divide each of those by m. So a mod m equals b mod m. This is also another way of saying when a and b are congruent to each other, modulo m, then there exists an integer k such that a equals b plus k times m. So when you add some multiple of m to b, you would get a. Obviously, k here can be a negative value or 0 or a positive value as long as it's an integer. Now, we have already seen this. Modulo m congruence classes are equivalence classes in a given set of integers. Okay, so next we have two very useful results, and I believe you might have been using this for years. Uh, Essentially, when you have integers a, b, c, d, m, where m, the modular value, is greater than 0. If a and b are equivalent or congruent modulo m, and c and d are congruent modulo m, then the sum of a and c and the sum of b and d are also going to be congruent modulo m. Also, the product of A and C and the product of B and D are going to be congruent modulo M. Okay, so this is a very useful result. Again, this is very easy to prove using the definition of congruence. And when you have two numbers, their remainders when divided by m, if you add them up and you take the remainder by m, that will be the remainder of the sum of the original two numbers. Same goes with the products. But one important point, the other way is not generally true. So you see the implication is this way. It's not biconditional. So for instance, if the sum of A and C and the sum of B and D are modulo M congruent, this doesn't mean A and B are going to be congruent and C and D are going to be congruent. It doesn't it's not guaranteed, but you have this implication in this direction only. Okay, so based on this theorem, we have this corollary. As I have stated now, if you would like to find the remainder of A plus B modulo M, what you can simply do is you find the remainder when you divide A by M, this, and then you find the remainder when you divide B by M, this, you add them up, and the result might exceed M, therefore you take another modulo M. The same goes for multiplication. If you would like to compute the remainder of A times B when divided by M, then you don't need to compute the product A times B. You can just simplify the operation by first computing the remainder of A divided by M, and then compute the remainder when B is divided by M, multiply them. Again, this product might exceed M, and therefore take another remainder when divided by M. Simple as that.